Okay, so today we're doing experiment number 11, which looks at the intermolecular forces present within molecules. Now, in order to determine the intermolecular forces present within molecules, you have to be able to determine the molecular polarity. Now, being able to determine the molecular polarity, you know you must be able to properly generate the Lewis structure and also the 3D model of the molecule itself. So with this experiment, you're going to have to look at various compounds and determine the intermolecular forces present. Then, based on the intermolecular forces present, you're going to have to discern which ones are the strongest and how those are going to affect things like rate of evaporation and also viscosity. So one of the things that you have to be able to do is determine the intermolecular forces present within molecules. Now, it's based on polarity, as I've mentioned, and just to kind of recap about intermolecular forces, we know that when we have a non-polar molecule, the intermolecular forces that are going to be present are the London dispersion forces. And if you recall, London dispersion forces are temporary induced dipole moments, dipoles. So if you think back about what a nonpolar molecule is, we know that you can have polar bonds or nonpolar bonds in a nonpolar molecule. What you're looking for here is whether or not there is a net dipole moment. Now, whether or not there is no net dipole moment. So, once you're able to determine the polarity of the molecule, then you can say, well, since it is a nonpolar molecule, there's automatically London dispersion forces present. And I generally abbreviate London dispersion forces as LDF. It makes it a little bit easier to write. But what these forces are basically are temporary induced dipoles of nonpolar molecules. Now, all molecules have London dispersion forces because all molecules have electrons. So all molecules have the capability of having these temporary induced dipole moments. Now, polar molecules, on the other hand, polar molecules because they have electrons and because you know this, are automatically going to have London dispersion forces. But since a molecule is polar, it's also going to have what's known as Dipole-Dipole forces. Which, instead of being a temporary induced dipole moment, is actually a permanent dipole moment. And we see that with polar molecules. We're looking for a net dipole moment. So it should make sense that dipole-dipole forces are permanent rather than temporary. So all polar molecules have London dispersion forces and dipole-dipole forces. So you can see why it's very important to be able to determine the polarity of the molecule. Now, the two additional intermolecular forces that we need to look at, one is a special dipole-dipole force, and only polar molecules have the possibility of having it. Okay, so dipole-dipole forces are found in all polar molecules. Hydrogen dipole-dipole forces are special, and not all polar molecules have them. What you're looking for is a bond between a hydrogen and one of three elements. You're looking for a bond between fluorine, oxygen, or nitrogen. Okay? So, if we look at these, we see all nonpolar molecules have London dispersion forces. All molecules, in fact, have London dispersion forces. Polar molecules have London dispersion forces and Dipole-Dipole Forces. And I oftentimes abbreviate this DDF. Then you have to look, is there a special type of Dipole-Dipole Force? And this is what's known as a hydrogen Dipole-Dipole Force, and I abbreviate it HDDF. And it's when you see within the molecule a hydrogen bound to either fluorine, oxygen, or nitrogen. Now in terms of strength, hydrogen Dipole-Dipole Forces is the strongest, Dipole-Dipole Forces is the next strongest, and then London Dispersion Forces are the weakest out of these three. There's one additional type that we have to look at, and this is what's known as an ion dipole force. And basically what this means is that you have a polar molecule. So you have to have a polar molecule. So you know right there, because you have a polar molecule, you're going to have London dispersion forces and dipole-dipole forces. Then you have to check, will I have hydrogen dipole-dipole forces? And you need to have something that forms ions in the polar molecule. So when that happens, we have the ion dipole forces. So ion dipole forces. And if you compare these types of forces to the other three, this one is absolutely the strongest. So then hydrogen dipole would be the second, dipole-dipole would be the third, and the London dispersion forces would be the weakest. So in terms of strength, the ion dipole force is the strongest out of the four. But you have to have certain criteria. You have to have a polar molecule, and you have to have something that forms ions. Okay, so think an ionic compound in water. Think an acid. Think a base. Particularly a strong acid and a strong base, because you know that they dissociate into their individual ions, thus forming ions in, you know, since they're an acid or a base, water has to be present. You've got your polar molecule, you know that you're going to have an ion dipole force. So this is a brief synopsis about intermolecular forces, the types that we need to look for, and their relative strengths.